Hi everyone, let's start section 2 of lecture 2. This section will be covered in two pre-recorded videos and this is the first part. On the course map, we are still in the inventory control category and we are in chapter 5. In section 1, we had um, the single inventory control model, which is called news vendor model. And in this section, we are going to have uh, uncertain inventory control models for multiple periods and assuming a continuous review of the inventory level. So in this section, we are going to have the lot size reorder point system. So in this system, we assume that we have multiple periods and also we continuously monitor the inventory level. So we'll have a reorder point in terms of the inventory level, and also we need to obtain the order size. So because of that, this model is called lot size reorder point system. Okay. In section 1 of chapter 5, we had the newsboy or news vendor model. And as you remember, this model is applicable for certain goods like the newspaper, like the fashion goods, like the seasonal goods, or perishable goods like the foods. So, for example, for newspaper, yesterday's newspaper has no value in the market, right? So this means that in the news vendor model, we assume that the goods may have no value at the end of the period, or they may lose a major part of their value at the end of the period. So, but for other goods, we don't have this assumption, right? In other goods, if we have unsold items in our inventory at the end of a period, then they will have their value in the next periods, right? So yeah, we can use them for sale in future. So on those goods, on those uh, products, we can't use the news vendor model. So we need to have another model, which here we call this as lot size reorder point model. And we're going to have this model in this section, and we'll apply the approach like we had for EOQ. So we can say this model is somehow an extension for the EOQ model by assuming uncertain demand. Okay. So let's see what are our assumptions in this model. At first, we assume that the inventory level is monitored continuously over time. So this means that we know the inventory level on hand at all times. Okay, and demand is random here. So yeah, demand is not constant, demand is random, but we assume that the mean and variance of demand are constant, which is an assumption for a stationary models. Okay, and here we assume that we have a positive lead time. So the lead time is not zero. We have a lead time, and its definition is the time period between placing an order and receiving that order in our inventory. Okay, and these are the costs. Like other models, we have setup cost here, $K per order, and also unit order cost, $C per each unit ordered, or let's say unit purchase price. And the holding cost, again, like the previous models, H per unit held per unit time, which is usually year. And but the penalty cost here is somehow a new cost. Yeah, we didn't have this in EOQ model because over there in EOQ model we assume that demand is constant. It's not random. So since we know the demand with certainty, so there is no reason to have shortage, right? So because of that, we didn't have penalty cost. But here, since demand is random, so we may be in a shortage situation. So for any unit short, we need to have a penalty cost here, and it's P dollars. Okay. So here we're assuming a random demand, right? So let's assume that this is our inventory level, and at this point, let's say we are placing a new order, okay? And let's say this is the lead time period tau, and here we may have different situations. We may, let's show with different color here, we may go like this, and then for this period we are out of we are in the situation of out of stock, right? So here we will have back order or lost sale. Or we may go like this, and here we will receive our order and inventory level jumps to this level and again starts declining. Okay, so as you see here, because of this, in these times, I can say there is no risk because we have enough inventory in our stock, so there is no risk. But the risk is in the lead time period, right? Because we have placed our order and we have to wait for the lead time in order to have our order in our stock. But during this period, we may be in shortage, or maybe there is no risk, but there is a risk, right? There is a risk for being in stock out situation. So because of that, we can say that since the only risk here is occurring during the lead time, so we can define the random demand for the lead time period. So yeah, because of that, we assume that demand over the lead time has a distribution, like let's say in general with fx, and the mu and sigma are defined like this for the demand during the lead time. Okay, and yeah, I mean this could be any distribution, but generally we assume a normal distribution because of calculation purposes. Okay. So in this model, we are going to optimize our decision on two things. The first thing is Q, and the second thing is R. So yeah, we need to optimize the order quantity and also reorder point, when to order and how much to order. So the answer for when to order is the reorder point. So here we show this by R, and this should be enough to protect against uncertainty of demand during the lead time, right? Yeah. So in order to formulate this problem, we will follow the same steps as a news vendor model. So at first, we need to define the expected cost function terms, and then after that, we will have an expected cost function, right? And then we will minimize that cost function in order to optimize our decision variables, which are Q and R, okay? The first term in the objective function is expected holding cost. In the EOQ model, if you remember, this was the expected inventory level over time, right? And the maximum level was Q, and so because of that, the average inventory level over time is half of Q, right? But here in the uncertain model, we have another term here, which is S, and S is the safety stock. So this is the safety stock at the expected level of on-hand inventory just before an order arrives. So I can say the safety stock is a certain level of inventory that we need to have in our inventory over time in order to deal with the risk of running to stock out situation during the lead time period. So yeah, because of the uncertainty on demand and risk of being short, so we need to have more inventory level. And I mean, the excess inventory level here that we have compared to the EOQ is called safety stock. Okay, so let's see how can we obtain the safety stock. So we have a reorder point, right? And then let me write here. So we have a reorder point. So reorder point is the level of inventory that whenever the inventory reaches to that level, we place our order. Okay, and then during the lead time, which is tau. I mean the lead time length is tau. Okay, and we know that the mean demand over time in the time period, I mean in a year, is lambda, right? So if we multiply lambda by tau, it will be a mean demand during the lead time, right? And then R minus lambda, I mean the reorder point minus the mean demand during the lead time will be our safety stock S. Okay, so if we set R, I mean the reorder point be equal to lambda tau, what happens? Here we are assuming that the reorder point is the mean demand during the lead time. That's exactly what we had in the EOQ model, right? Yeah, in the EOQ model, we just multiplied lambda by tau, and then that was our reorder point. Because in that model, demand is constant, right? But here demand is random, but the mean demand is lambda. And if we set a reorder point exactly be equal to lambda t, I mean lambda tau, the mean demand during the lead time, then let's say demand over the lead time is normal, okay, with mu and standard deviation of sigma, okay, sigma. So if we set the reorder point exactly to lambda tau or mu, then with 50% chance, which is here, 50% chance, demand could be greater than the mean, right? Then with 50% chance, we will have stock out situation, right? So because of that, we are actually accepting a higher level of risk to be insured during the lead time if we set R equal as lambda tau. But in order to mitigate with this risk of being short, we need to consider R greater than lambda tau. So, but for how much, it depends to what level we want to have. We want to have for safety stock, and it can be obtained by the probability. I mean, we may assume that we want to have enough inventory to satisfy, let's say, at least 95% of demands during the lead time. And then based on that, we will obtain the R. Okay, so yeah, by having that, so if we obtain R by assuming that probability, then, and also we know that the mean demand during the lead time is lambda times tau or mu, then R minus lambda tau will be our safety stock. Okay, so now we have an S here, and also we have a Q here. So the maximum level of inventory becomes S plus Q, right? And so the average level for inventory becomes S plus half of Q. This is the average level for inventory. Okay, yeah, we do have it here, S plus Q over 2, or we can replace S by R minus lambda tau time plus Q over 2. Okay, and now if we multiply this average level of inventory by H, it will be the expected or average holding cost, okay, which is here. Oh, sorry, which is here. Okay. The second term in the objective function is the expected setup or ordering cost. So here there is no difference between this model and the EOQ model, because here we're assuming that the order quantity is Q, and if we divide the mean demand over the year lambda by Q, it will obtain the number of orderings per year. So, or if we assume that the T is the length of the cycle, I mean, cycle length is the time between two consecutive orders. Okay, so lambda over Q will be equal to 1 over T. I mean, if you have the cycle length, then if you divide 1 by T, you can obtain the number of orders, or you can divide lambda by Q. So the T, the cycle length, is Q over lambda. Okay, so now the average annual cost for ordering or setup cost will be K times lambda over Q, or K divided by T. So why we do have these two terms here? Because if we are going to formulate our problem in terms of Q, I mean the quantity for ordering, then we will use this term. We will use this term, K times lambda over Q. But if we are going to formulate the problem in terms of the cycle length, then our decision variable becomes T instead of Q. Then we will use this this term in our objective function. Okay, so in this part we had these two terms. In the next part we will have the term for expected penalty cost, and then we will have the objective function, and then we'll see how we can obtain the optimal value for Q and R. Okay, thank you.